we have seen that there are charges and charges exert force on other charges. We saw a heading called as electrical field, which talks about what does this charge or bunch of charges put together, how do they change the space around them, what kind of field will they create. So that we call it as electrical field. Now we'll start off with taking a dot and understanding how it affects the field around it, and in time we'll be looking at two dots, bunch of dots with help of superposition theorem, and then continuous charge distribution, the field created by this using our integration, and so on and so forth. So then we look at a disk, a ring, so on and so forth, sphere, right? Again, what is that we're talking about? Just close your eyes and think of the sequence. Think of a charge. Think of another charge. They are pulling or pushing each other. With what force? You guys know the formula. Now, that second charge disappeared. You have the first charge. Along with that, they can be made up of bunch of charges, which is lined up on a wire or a ring or a disk. It can be anywhere. Again, keep imagining. Now we're looking at how does it affect the region around it, space around it. If it's just a dot, what happens? We're starting off with that. If there are two dots, what happens? If there are a bunch of dots, that is continuous set of dots, what's going to happen? This is what we're going to study now. So now you can open your eyes. Let's look at the screen. So we have a dot, right? Like sun, we know that sun radiates out light equally all around, at least most of the time. Charge to a single dot charge will also affect the space so that it's radially outward. That is, it is spherical in nature in some sense. Can we tell that? Common sense tells that its electrical field will be in the shape of a sphere. Agree? So basically we're looking at force exerted by a point charge all around. So again, we're just starting with a dot, then we look at two dots, then we look at bunch of dots. So first thing first, let's have a diagram. So this is the charge which we are studying. And this is the point wherein we are trying to understand how this charge, which is of charge Q, will affect this. So what do we need? We need a test charge placed at that point, say Q naught. So this is basically our source charge, and that's our test charge, right? So this would be our distance. And if this is positive and that is also positive, this has to be positive, test charge has to be positive, and say this is also positive. That would be the direction of force, and the same funda for your electrical field also. So let's represent this as R cap. Okay, that's the unit vector pointing along the line connecting Q and Q naught. So as per Coulomb's law, the force on charge Q naught is given by K Q, capital Q actually, Q naught by R square. In form of vector, we just have to do this. This is from Coulomb's law. Agree? Now, the electrical field, which is given by divided by test charge, will be equal to K Q by R square along the line connecting Q and Q naught. Agree, guys? So this is your mathematical aspect of a point charge. It's a very simple thing. It's the same formula that we have seen. So let's analyze this. Again, this is an official introduction. So that basic idea is just a statement that is in my head, right? So here in that formula, we saw that, and we can see that E is proportional to square of the distance. So all points on a spherical surface drawn around a point charge have the same electrical field strength regardless of direction. What it means is, if I take a point charge, if I draw a sphere, on that sphere, the magnitude of electrical field will be same. Again, we are trying to study the pattern which the spheres, not spheres per se, but any kind of charge will create around it. Again, we are trying to understand the shape. We're trying to learn the pattern, right? So the pattern over here is what? It's spherical. Therefore, the field is referred to as spherical symmetry or radial field. Simple. You have a dot. You are looking at a sphere with this as a center. So this, at this point, the magnitude of the electrical field will be the same. Agree? Right? Because the distance will be the same, Q is the same. So by default, the strength has to be the same. Direction is different. And because of this, we can tell that a point charge creates a spherically symmetrical electrical field, also called as a radial field. Right, guys? I hope you guys are able to link. Again, get the big picture. If not, this is just a simple expression and you are done. But get the big picture. What is the big picture? We have charges. Charges exert force. And now we are trying to study the pattern that this charges create. And that heading is your electrical field. We got introduced to the basic idea of electrical field. It's not a big deal. It's just that it's forced by the test charge. Now, we are looking at the first pattern, a pattern created by a point charge. Very simple thing. Thinking of, say, we can think of the sun. Sun radiates out light equally most of the time, that is. Of course, there is a lot of variation. Let me come back. Ideally, the sun radiates out energy equally, and this shape is spherical. So this is called a spherical symmetrical or radial field. Why? Because the electrical field on any sphere with center being the point charge, the electrical field E1, E2, E3 in terms of magnitude will be same, because they are at equal distance from the center, right? As R is same for the 3. Okay, guys. Right? Again, understand the pattern, what we are trying to study over here. It makes it fun and easy. If not, it will be a dry subject.